Hello everyone, my name is Yi Xiao from Wuhan University. Today I'm presenting our ICCV oral paper. The title of our work is GM Mamba, Group Masking Mamba for Host Light Image Classification. I will introduce our work from four aspects. First, there is the introduction section. Pathological tissue images reveal important tumor structures and are the golden standard for career dinosaurs. However, in clinical practice, examining these complex structures under the microscope is often time-consuming and labor-intensive. With the development of digital scanning, traditional slides can now be converted into multi-level, high-resolution digital pathology images. Combined with deep learning, this has greatly advanced computer-aided dinosaurs. However, because whole slide images have gigapixel resolution, with sparse tumor regions and complex tissue structures, collecting fine-grained annotation is extremely challenging. As a result, researchers have shifted toward weakly supervised learning that only requires slide-level labels. Multiple instance learning is one of the mainstream weakly supervised methods. In multiple instance learning, we treat a whole slide image as a bag and cut it into tens of thousands of small patches, called instances. The model is trained with only slide-level labels as supervision. The main pipeline includes instance sampling, feature aggregation, and final prediction. Effectively aggregating global instances is critical for obtaining accurate and robust feature representations, which in turn improves prediction accuracy. To achieve this goal, most methods rely on attention machines or transformer to aggregate feature and capture key information. However, attention and transformer-based multiple instance learning methods are limited by uninformative instance and heavy computation, which leads to suboptimal representations and slow inference. Recently, thanks to Mamba's advantages in global modeling and its linear complexity, Mamba-based multiple instance learning methods have become a growing research focus. Despite this, there are still two major challenges in pathology images. First, redundant local modeling. Bag-based Mamba treats all instances equally, leading to unnecessary computation from non-discriminative features and possible loss of critical information. Secondly, sparse global representation. Tumor regions in whole slide images are spatially sparse, making it difficult to aggregate discriminative features across groups. Current methods inadequately model intergroup correlations, which impairs global representation. Second, it is the method section. To mitigate the aforementioned limitations, we propose a novel group masking member called GM member for whole slide image classification. GM member mitigates undesirable local redundancy through an intra-group masking member called IMM module and enhance global representation through cross-group superfeature sampling called CSS module. Firstly, GM member employs a location-based clustering scheme to generate instance embedding. Secondly, to eliminate redundant and irrelevant instances within these groups, IMM module adaptively uses learnable sparse masks between bidirectional member blocks to dynamically eliminate low-attention features. This enables member to focus on silent instances while enjoying the merit of linear complexity, resulting in efficient yet compact local representations. Finally, we employ we explore the correlation between group features with the proposed CSS module and perform prediction through multi-head attention and the MLP layer. Specifically, CSS module aggregates discriminative features from spatially dispersed tumor regions by first using max pooling to extract the most silent features for cross-attention calculation. To better capture complex intergroup relationships, a multi-head attention machine and an association matrix are then employed to refine these superfeatures into robust global representations. Next, it is the experiment section. To evaluate our method, we compare it with 12 widely used multiple instance learning approaches, including attention-based, transformer-based, and member-based methods. The comparison metric include AUC, accuracy, F1 score, precision, and recall. We evaluate our GM member on 4 widely used whole slide image dataset. Here, we show that the proposed GM member consistently outperforms existing methods. For example, compared with attention-based multiple instance learning method, we achieve 1 to 2.2% higher accuracy and F1 scores. On the TCGA ESCA dataset, we gain 6.4% in accuracy, 5.4% in F1, and 2.2% in AUC. Importantly, while compared to the member-based baseline, our model achieves 12.8% improvement in accuracy, thanks to its ability to reduce redundancy and enhance intergroup interactions. In the ablation section, we assess the impact of some key components, including location-based grouping, bi-directional member with max pooling, the proposed IMM module, and the proposed CSS module. By using IMM as CSS modules, the model can improve the local and global representation respectively, and the final GM member achieves the best performance. Additionally, we validate the effectiveness and generalizability of our proposed CSS module. It can be seen, CSS module improves the performance of various back-level methods. It is plug and play, boosting the performance of attention, transformer, and member-based methods. We further validate the CSS module by setting different variants. As shown in this table, our CSS module consistently outperforms its variants, and the association matrix Q can effectively bridge local and global interactions, resulting in stronger group representations. Finally, we analyze the hyperparameter settings, such as the number of groups, the masking rate. We can find that by clustering instances with similar tissues and structures, the proposed GM member can reduce redundancy and generates more precious back representations. Besides, the masking rate is an important hyperparameter. It should not be too large or too small, and different settings need to be adopted for different datasets. Last, it is the conclusion section. The key innovation of this work lies in the IMM module, which address local redundancy and enhance group representations. We also introduced the CSS module to aggregate dispersed tumor information, results in more comprehensive global representations. While our proposed GM Mamba achieves favorable improvements, its performance is still limited by using the same masking rate across different groups. Thus, future work could explore learnable or dynamic masking strategies, further enhancing robustness. Thank you for your listening.